Good morning everyone, and welcome to today's worked exam answer post. Today I'm taking a look at a reacting mass and percentage yield calculation which has come from an Edexcel iGCSE past paper. However, these are both skills that will also be assessed on the AQA GCSE and are also skills that you will still need to be able to do for those of you studying A-level AQA chemistry. So as always, I'm going to use two different colours to highlight the different parts of each of these two separate calculations, complete my worked answers, and then explain everything in detail to you guys. Okie dokie, so the first part of this question I have termed a reacting mass calculation. That is a type of question where we are given the mass of one substance from a balanced chemical equation and we have to use that mass, calculate the moles, then use the mole ratio from the balanced chemical equation to enable us to work out the mass of a second substance in the equation. So the equation that we've been given shows how tungsten, which I've used pink for, can be obtained by reacting the tungsten fluoride in the turquoise with hydrogen. And they've given us this balanced chemical equation, and we're wanting to find out the maximum mass of tungsten that we can make from a particular mass of the tungsten fluoride. So I've highlighted the tungsten fluoride and everything in the question to do with the tungsten fluoride in the turquoise and everything to do with the tungsten in pink. Now we can see that there's no balancing numbers in front of either of those species in my balanced chemical equation, which tells me that the ratio in terms of how many moles of tungsten fluoride would react and make the same number of moles of tungsten is in a 1-to-1 ratio. We get told that we're starting with 59.6 grams of tungsten fluoride, and we get given the relative formula mass of the tungsten fluoride as well. From those two pieces of information we can get the moles, then we can use the ratio to get the moles of the tungsten, and then we can use the AR of tungsten to get the mass. Now you do not have to lay your workings out in this table format as I have done, but I think this is the clearest way for me to demonstrate how to do this. So I've got my two column headers, so my tungsten fluoride, so that is what we have information about. We know that mass, we know that MR. Then the second column header is my tungsten, because that is what I want to find the mass of. And we then have a row for mass, a row for MR/AR, a row for moles, and a row for the ratio. And using the mass and the MR that we were given for the tungsten fluoride, we can work out that the moles of tungsten fluoride that react is 0.2. Because the amount of tungsten fluoride that reacts and the amount of tungsten made is in a 1-to-1 ratio, that means that we also are going to make 0.2 moles of the tungsten. Tungsten has a relative atomic mass value of 184, which you can get from the periodic table. And then to get the mass of tungsten that can be made, we need to times those two together, the moles by the AR, to get the mass, which is 36.8 grams. Now, the reason why it says maximum mass of tungsten is because this calculation tells us if all of this tungsten fluoride was to react, that 36.8 would be the most amount of tungsten we could possibly hope to make. Now, we find that very rarely do we get anywhere near making 100% of the mass that we have worked out that we should be able to make. And that's where percentage yield comes in. Percentage yield is a measure of the practical efficiency. So how much should we have been able to make in this experiment, which we always work out using one of these reacting mass calculations, versus how much mass did we actually make. Now, that isn't to say that that is our fault as humans. It's procedural errors that account for loss of mass, but it's a really helpful calculation for us to be able to work out, to say, okay, so out of the maximum I thought I should have been able to make, I actually only got this. So the next question, where we're thinking about different values, because we're starting with a different mass of tungsten fluoride here, the student calculates that the mass of tungsten formed should be 52.0 grams. So that is our theoretical maximum mass, which we worked out from the previous information for the last question to be 36.8. That would have been our theoretical maximum mass there. Here, we've been told it's 52 grams. In his experiment, the student actually obtains 47.5 grams of tungsten. So that is the actual mass, and the wording here is quite helpful because they've said that he actually obtains. So that is our actual mass. And then to calculate the percentage yield, we take the value for the actual mass, divide it by our theoretical maximum mass, and times it by 100 to get it as a percentage. So we're going to be doing the 47.5 grams that we actually made, divided by the 52 grams, which was the maximum we could have hoped for, times that by 100, and we get a yield of 91.3%. Now I've chosen to give that to one decimal place or 3 significant figures because that was the number of decimal places / significant figures in the question. 91.3% is a good yield. It's very unusual to get a lot higher than that, certainly to get, much closer to 100, but it is the case that some reactions that we still do in industry have quite a low percentage yield, simply because there is no better way for us to do that experiment as of yet. So that is how we would do a reactive mass calculation, and how we could then use our reactive mass calculation to work out the percentage yield. If anybody has any questions about the content of this video, please do not hesitate to ask. I am more than happy to help. Thank you so much for watching, guys. Hope you have a really lovely day.